Today, we will see some of the synthesis techniques used for preparing nanoparticles, which are used for specific applications, and how the prepared nanoparticles can be characterized. Characterization in the sense relevant characterization, and most of you who are working in the related area might be knowing that for any nanoparticle, it is necessary to have the term characterization to see exactly the particle size, right? Okay, so then I will slowly move into the epitaxy of the semiconductor nanostructures, and finally, maybe the device structure what we have prepared related to the light emitting diode. Okay, so this particular slide gives you details about the copper oxide nanoparticle preparation, and the morphology of this particular nanomaterial seems to give us very interesting results in the sense the morphology is presented posed a lot of issues for us to investigate further in this particular area. And later on, we felt that the floor-like morphology shown by the copper oxide, which was synthesized using the simple hydrothermal technique or solvothermal technique, gave us confidence in proceeding further to completely replace the currently used exhaust catalyst materials based on platinum group metals, which are very costly and found to be abundant in nature. So this way we were able to replace the currently used platinum group metals as a catalyst for detecting the exhaust gases. So the platinum group metals, in the sense platinum, palladium, rhodium, these are all very costly materials. So they are being used as the exhaust catalyst detectors, how much of nitrous oxide, carbon dioxide, or the other gases are present when, say, for example, an automobile is used. Right. So we'll move on to this particular topic quickly, because yesterday we had 1 hour minus, and today I got to compensate. So that particular 1 hour, in addition to the other topics to be covered. Okay. So this non-platinum group metals, they are non-PGM catalyst because they are very cheap and abundant, and they have very high surface area with no thermal agglomeration. The problem is that with this platinum group nanoparticles, which are used as the exhaust catalyst, they have very good relative surface area, but with respect to time, due to thermal agglomeration, there is a decrease in the surface area. Then, because of the decrease in surface area, there is carbon corrosion and loss of nanoparticles. Hence, finally, end up with a decrease in performance and durability. So, I will have to look for the certain non-PGM group materials which can completely replace the platinum, palladium, or rhodium based materials. So, in this aspect only, we have tried this copper oxide. So, whatever you do, before you prepare, you have to think a lot in terms of its applications, because we can publish papers in impact factor journals, but what is the application? Because now the competition is very high, so you have to show yourself in a different way. So when you try to prepare a material, you have to understand its the applications, in what way it can be applied in future. You can go for a patent, or you can go for a product. So in that way, we have to think a lot, because the competition in the future will be very, very different, totally different. So we have to somehow come up in life, as life in the sense and the research, and particularly in academics. So the non-PGM group metal catalyst will exhibit what is called a high surface area with no thermal agglomeration, and they also show high catalytic activity and selectivity. So hence you have what is called as the increased performance. Okay. So what we have thought is that if you use microcrystal, that is a three-dimensional crystal, so it has different phases, different orientations, different phases. So certain phases may be useful for the desired reaction, and most of the phases may not be useful for desired reaction. That is what is shown in the picture. So in a particular phase, FACE, the desired reaction are welcome, whereas in other directions, orientations, or phases or phases, we expect undesired reactions, maybe due to low surface area. So we have to think in terms of choosing a particular phase and try to going for analyzing further in terms of a device application or a product. Okay. So if it is a two-dimensional crystal, the advantage you have is that if it is a two-dimensional crystal, the advantage you have is that you have only one particular phase being exhibited, and that particular phase is the desired phase for reaction to take place, catalyst reaction to take place. Then it will be very, very advantageous because the reaction can be selective and it can exhibit very high surface area, and thus you can try to avoid the undesired phases or phases which are not useful for the desired reaction for this catalytic activity. So we'll move on to this the synthesis part of the copper oxide nano platelets. Here we have chosen this hydrothermal technique, or it is also called as salvothermal technique. We use for synthesis of copper oxide, we use copper chloride plus urea, and the hydrothermal synthesis was done at 140 degree. Yes, 140 degrees centigrade for 15 hours, and water and ethylene glycol were added. So, and finally, we end up with interleaved copper oxide nanoplatelets. And yesterday in my lecture, I was telling about the three dominant factors: high surface reaction, ubiquitous Brownian motion. Then the other one more point I was telling, maybe might be remembering. So one of these three factors, they try to give you variation in morphology when you're going for such a chemical route synthesis. So the typical Teflon lined stainless steel autoclave is shown here, and the typical XRD pattern is also shown for various mixing ratio of water and ethylene glycol, various ratios 5:3, sorry 5:0, 4:1, 3:2. And here copper chloride and urea was added in the ratio 1:1. Reaction temperature is 140 degrees centigrade, reaction time 15 hours. So for various reaction temperature and copper chloride urea ratio, we prepared the copper oxide nanoparticles. So with water and ethylene glycol, with water and ethylene glycol at a different ratio for a particular reaction temperature, and we kept the reaction time to be 15 hours, and the copper chloride and the urea was taken in the ratio 1:1. The related SEM picture is shown here. FESM picture is shown here, so you can see the morphology of this nanoparticle, copper oxide nanoparticle. It shows floor-like morphology, and the student who did this work, her name is also Malar in Tamil. Malar means English flower. So there is the typical correspondence between name and the morphology of the copper oxide she prepared, and you can see the high magnification of this the flower morphology, individual petal-like structure, and later on we try to analyze each petal or each platelet and try to analyze further to see which phase is suitable for the catalytic reaction. Then this picture gives for the other ratios of water ethylene glycol. Then once again the XRD pattern for various reaction times, 18 hours, 15 hours, 12 hours, varied from 1 hour to 18 hours. And finally, we found that yes, the optimum condition for the preparation of copper oxide floor-like morphology is found to be 15 hours. Reaction temperature to be 140 degrees centigrade. Water to ethylene glycol ratio is found to be 3:1. Once again, the copper chloride urea, the initial the reactants ratio to be 1:1. Now you can see once again the beautiful floor-like morphology. Now it is our duty to analyze the floor-like morphology. The nanoparticles will have to individually pick out the petals and try to analyze. So then only you can think of going in for the study related to catalytic studies. So for this, what you have done is we have done focused ion beam study to pick out a single petal and try to analyze using the transmission electron microscopy and later the diffraction studies. So we using FIB, focused ion beam, we smash this particular floor-like morphology, pick out a single petal, and this single petal seems to be a single crystal as shown in the electron diffraction pattern. And the size of this petal is around 50 nanometers. Thickness is found to be 10 to 15 nanometers. And the fringe pattern taken using okay. So the fringe pattern shows that it is a single crystalline material, and the lattice spacing can also be interplanar spacing is found to be 2.71 angstrom, and it corresponds to 110 orientation, and the perpendicular to this 110 orientation is 010. And now we will have to cut small portion of this 001 copper oxide platelet for TEM observation. So this will be typical the platelet at high magnification, and out of this we are able to cut a small portion of this platelet for further TEM observation. So you can see the lattice, the fringes at a higher magnification, and the interplanar spacing is found to be 2.5 angstrom. So the orientation is the along the basal plane it is 001, perpendicular to is 010 phase. Now we'll have to see which phase looks better for the reaction, and using XPS also we can try to confirm the nature of the copper oxide nanoplatelets. So the peaks at 934. It is compared with the copper oxide standard, and the star indicates the typical the binding energy value for pure copper 2, that is copper 2 valency. Now we try to calculate the surface area of copper oxide using the bed krypton bed analysis, that is krypton absorption value. So the interleaved copper oxide nanoplatelets show very high the surface area, that is 29 meters square per gram, and the commercially available copper oxide nanoparticles show 19.8 meters square per gram. that is which is available in the market, and the FEM analysis of this the flower like morphology after plot various the temperatures, the change in the morphology with various temperature because it has to withstand the catalytic reaction at high temperature also. So at 195 degrees centigrade, 260 degrees centigrade, 900 degrees centigrade, and the corresponding the morphology. And we have also compared the various copper oxide based nanoparticles for comparison in terms of their the morphology. So here we use copper oxide urchins, then copper oxide thick plates, copper oxide nanoplates, then copper oxide petals, then copper oxide nanoparticles, the particle size being less than 50 nanometers. So here the copper oxide 001 phase seems to be a good phase, and the other phases are bad in the sense they are not that reactive for the catalytic action, and moreover, the copper oxide 001 phase exhibits very high surface area, and the surface is almost 001 orientation as determined through HR temp, and this nanoplatelet was used for detecting the volume fraction of nitrous oxide absorbed from the gas coming out of the exhaust of the automobile, and it seems to work very well. It is able to absorb sorry, a very high fraction of nitrous oxide. Here, as per the graph, the y-axis gives the volume fraction of nitrous oxide absorbed in ppm and versus the duration. In 15 minutes, it is able to absorb nearly 300 ppm of the nitrous oxide. So it was done using 86 ml diesel gasoline engine with a 2.4 horsepower at a revolution of 3,600. So this copper oxide is now can be replaced replaced to that of the PGM catalyst, that is platinum group catalyst. So the copper oxide based on nanoparticles are more economic. It is abundantly available, and it is not costly. So this is a patented work published as well as the patent. So whatever we try to do, the application becomes very important. And the other important thing is that we have to characterize and achieve that the results gives you the authenticated values for proceeding further in terms of the related application. Okay. Then comes what is called as the doping up cerium oxide with copper oxide, or the cerium oxide copper oxide composite for the further application. So here the structure of interleaved copper oxide nanoplatelet was not disturbed during the synthesis. So we just added cerium chloride heptahydrate, or you can also add ammonium cerium nitrate, or you can also add copper chloride dihydrate for copper and urea. The same 140 degrees centigrade were used, 15 hours reaction, and water to ethylene glycol ratio was 3:2. Once again, the same microthermal reaction, the related XRD pattern for various 8% of cerium oxide and copper oxide. Then the related the morphology of the cerium oxide when it is doped with copper oxide. Then comes the EDAX analysis to see whether cerium is inside or not. Then comes the XRD pattern of cerium oxide composite from Serium 4 plus precursor for different weight percentage, 5 weight percentage, 2 weight percentage, and 1 weight percentage. Then the morphology using Serium for this the composite for different weight percentage of the Serium oxide. Then comes the the synthesis of copper from copper oxide. So here we use the high temperature of 250 degrees centigrade and pass hydrogen gas so that the when copper oxide mixes with hydrogen, it forms copper as well as the water. Okay, so you end up with microporous the copper at room temperature. When the interleaved copper oxide nanoplates are added to the sodium NaBH4 for 24 hours, you also end up with interleaved mesoporous copper nanoplates. So depending upon the type of reaction you use, you end up with microporous or mesoporous copper nanoplatelet. And once again, the related XRD studies for various reaction times and temperature, and the morphology for FACM for hydrogen gas reduced interleaved copper oxide nanoplates, because by passing hydrogen gas reduction the copper oxide takes place. And, for various concentrations of sodium BH4 reduction of interleaved copper oxide nanoplatelets for various concentrations. Then comes the morphology for various mole percentage of NaBH4. Here you can see that the floor-like morphology is not completely changed. They are trying to keep up the floor morphology so that it is possible for us to take one petal out of it, single crystalline petal, and try to do the analysis. Then comes the term analysis, term as well as normal term for macroporous and mesoporous copper. The mesoporous copper seems to be exhibiting polycrystalline with a grain size of around 2 nanometers, and the pore size is about 5 nanometers, whereas the macroporous copper exhibit a single crystalline matter as shown in the exact picture with fringy pattern seen in sleep. The grain size is greater than 20 nanometers, more than 20 nanometers, and the surface area seems to be 4.93 meters square per gram, whereas in the case of mesoporous copper, the surface area is 8.16 meters square per gram. Okay. Then comes the redox analysis for this the microporous as well as mesoporous copper. Then the XPS analysis to see the status of copper. The 932 point electron volt peak and 952.6 electron volt peak corresponds to single spin orbital pair with 2332 and 2312 nature of metallic copper, and this shows that the reaction what you have taken is optimum. Then comes our important topic, that is the epitaxy. So here the important point is that nowadays most of the optoelectronic devices are prepared using the epitaxy only. Though it is easy to prepare nanoparticles using chemical route, which is not very costly, and which is when optimized becomes very easy. But the problem is that these the nanoparticles cannot be used for the preparation of most of the optoelectronic devices. So that disadvantage we have. And in the epitaxial growth technique, though it is very costly, it is possible for us to prepare the up to 60 to 70% of the device structure during growth itself, and later on we'll have to go in for completing the structure using say partly due to lithographic technique and other chemicals. You need to go in for metal contact analysis. The moment you think in terms of epitaxy means single crystalline layer on a substrate that is extended single crystalline film formation on top of the crystalline substrate. So you use a single crystalline substrate, and on that you try to grow film. Film means it means both polycrystalline as well as single crystalline material. It is epitaxy. It means only single crystalline layer. So if you talk in terms of epitaxy, you come across two different types of epitaxy, homoepitaxy and heteroepitaxy. If it is homoepitaxy, you try to grow, say, for example, germanium on germanium substrate, you call it as homoepitaxy. Instead, if you grow germanium layer, epitaxy layer on silicon, then it becomes heteroepitaxy. So gallium arsenide, epitaxy layer on gallium arsenide is homoepitaxy, and indium phosphide on gallium arsenide, you call it as heteroepitaxy. You can see some examples also. And here, the important parameter is that we have the interface between the grown epitaxy layer or film and the substrate. So the interface plays a dominant role in deciding whether you have two-dimensional growth or three-dimensional growth. It decides about whether you have a layer growth or the island growth, because the quantum dots are also grown using epitaxial technique, and here preparing quantum dots is a very tedious process. But once you optimize for a particular system, whether it is binary, ternary, or quaternary, then it becomes more compatible, and most of the industries adopt either MOCVD, that is MOPE, or MBE, that is MOMBE, metal organic molecular film epitaxy, or metal organic chemical deposition, or metal organic chemical epitaxy. Okay, so here in homoepitaxy, the lattice parameter of the grown layer or the epitaxy layer gets matched with the substrate. So at the interface, there will not be any strain or stress present. For this, you have to completely optimize. Though you call it as homoepitaxy, you have to optimize the growth conditions. Otherwise, at the interface, a small misfit dislocation, or what is called as lattice misfit or dislocation, will create large amount of stress or strain, and which will deteriorate the characteristics of the device fabricated using this structure. Say, for example, for LED, we need to have PN junction. Then, when you give the forward bias to proper metal contact, you have the electron hole pads created the interface, and finally they produce photons. And depending upon the nature of the biasing and the external voltage, you have what is called as spontaneous as well as simulated emission. So either LED or the laser diode. So the then comes the what is called as heteroepitaxy. In heteroepitaxy, you have both strained heteroepitaxy and relaxed heteroepitaxy. Relaxed heteroepitaxy. So heteroepitaxy, in the sense you have different the semiconducting materials being used. Say, for example, indium phosphide, as I told you earlier, indium phosphide and gallium arsenide. So these two materials have different lattice parameters. So you have to be very careful when you do the epitaxy layer of indium phosphide on the gallium arsenide substrate. So at the interface, because of the lattice mismatch, we will have the stress or strain present. Sometimes if the strain is large or stress is large, you will have a structure like this. So there will not be any lattice matching. You will have lattice mismatch. So if there is lattice mismatch, you have the stress, and hence you have what is called as the strain. But in certain cases, the strain can get relaxed after a few layers of growth. You can see here there is the first layer is lattice mismatch, and later on, because of the relaxation of the strain or stress, we get relaxed, and lattice matching comes into picture. So this we have to optimize, and the lattice misfit. Hello, lattice misfit or the defects at the interface can create a lot of issues as far as the device characteristics are concerned. So the lattice relaxation or strain relaxation or stress relaxation depends upon the critical thickness. So beyond the critical thickness, the stress or strain is totally relieved, and it varies from material to material. Okay. Now, this is a typical example for Epitaxy. So here you see the germanium growth on epitaxial layer growth on germanium, and the growth is for different partial pressure up here, because here for germanium source we use isobutyl germanium. So this metal organic decomposes, or the pyrolysis occurs at low temperature, and you get the germanium mm, atoms, and it gets deposited on the germanium substrate. And because it is epitaxial growth or CPD growth, we need to control the partial pressure. So either we keep this partial pressure constant and vary the temperature. So here the partial pressure of isobutyl germanium is kept constant as 1.94, 110 power minus 5 bar, and the growth is done at different temperatures, and the corresponding morphology is shown. This is the typical example for the Epitaxy. Only in that aspect I am showing this the picture. So here the crystallinity increases with increase in growth temperature, as shown in the AFM picture, and the roughness also keeps on decreasing as you increase the growth temperature. The fluid at maximum for germanium for the sample 3 is comparatively higher due to influence of growth temperature. So for first for 600 degrees centigrade, the fluid at maximum is 14 arc second, and for 650 it is 16, and for 675 it is 81. It increases enormously, right? Okay. So the growth at 600 is not so uniform, confirmed from the roughness values, because if you see the roughness for 600, though the fluid at maximum is very less, the roughness is very high. So you have to compensate with so many parameters and optimize the conditions. And here, see, previously the pressure, partial pressure was 1.94, whereas now we have adjusted the partial pressure to be 2.286 10 power minus 5. And see the germanium layer, epitaxial layer grown on germanium substrate, they almost get matched with the substrate peak, because in XRD, irradiation X-ray diffraction, you will get the peak for both epitaxial layer as well as for the substrate. So the orientation is along 004. See, the two samples almost have same peak with the different, though different fluid at maximum, there is no lattice mismatch. So this is a typical example for Epitaxy, that is germanium and germanium, provided you try to optimize the growth conditions. Say, because it is the elemental germanium semiconductor growth on germanium, and you have to be very careful in adjusting the growth parameters, temperature, everything, etc. So when you think in terms of binary, ternary, quaternary, you can understand the difficulty involved. The exotic profile coincides with that of the substrate can be considered as a perfect crystal. So for Germany substrate, the fluid at maximum is 11.5 off second, and when the growth temperature is varied at 550, it is 6 hours second, 675, it is 12.6 second. So it is a perfect lattice match, and it's a typical example for the home epitaxy. So for home epitaxy, I am giving this example. Then comes Electro Epitaxy. It's a typical system is Indian gallium phosphide epitaxial layer. So here you can see the mismatch here, the mismatch for epitaxial layer of Indian gallium phosphide to grow Indian gallium phosphide because the composition is not given. The Indian gallium phosphide, they exhibit indirect band gap for most of the compositions. If you take indium phosphide and gallium phosphide as the binary system, so it is a ternary system, indium X, gallium 1 minus X P. So in that way, we have to do it. So the center picture gives what is called as the typical HRXRD, the picture, and the right hand side AFM picture, that is, it corresponds to the roughness for the 600-degree growth. The roughness is 20 nanometers, and for 600, when it is doped with the silicon, the roughness increases from 20 to 51 nanometers. So the presence of strain release with the peak broadening is contributed to compositional variation when doping with the silicon. So, but here this slide is shown for as an example for Electro Epitaxy. Okay. Then comes in the case of Electro Epitaxy, what are the issues we come across? Say, for example, in the case of the Indian gallium phosphide and germanium. Germanium is a substrate. So here we see the transmission electron microscope cross-sectional view along 0.011 direction. So here you can see this is the interface. This Germanium substrate, and this line represents the interface. And here you can see on the Indian gallium phosphide epitaxial layer V-like pattern, and this V-like pattern shows the defects present in the system. On the right hand side, it shows the high resolution HR term, and where it gives clearly the twin boundary, right? And here the growth temperature is 650 degrees centigrade. Though the electron diffraction pattern shows this to be a layer, you still have what is called as defects like twin boundary. So here in the case of the defects appear bright in dark background, and defects are bright stripes inclined in V-shaped configuration. These are all normal defects that comes along in the case of 3-5 epitaxy, but you have to overcome by modifying the growth condition and avoid the defects for useful device configuration, device structure. And the other thing is that in germanium silicon, the problem is with antiphase domains. So the presence of antiphase domains and the lattice defects such as twins and stocking faults. So indium phosphide and gallium phosphide, they have the stocking fault energy is very less. So you have the stocking fault, the defects also come into the picture in terms of twin boundaries, and these twins preferentially gets nucleated near APB, that is antiphase domain boundaries, that is 30 to 50 nanometers from the interface, that can be clearly studied using HR term. The distance can also be calculated. So for this structure, for this system, it is around 30 to 50 nanometers from this is the interface and thin boundary. Okay, so this behavior is not dependent on temperature, but it is due to some instability in the gas phase. So I will tell you why you get the instability in gas phase. So when you see the reactor geometry, you understand the difficulties involved during the epitaxial growth, that is particularly in MOAPE and not in MBE, because in MOAPE you have what is called as the problem due to convection, then convection, conduction, and radiation can also change the characteristics of the structure we are drawing. Okay. The moment you think in terms of epitaxy, there are different types of epitaxy, liquid phase epitaxy, molecular beam epitaxy. Molecular beam epitaxy, there are two types, solid source, because those days they were using solid sources, and by suitably heating, they vaporize, and these vapors are sent to the substrate. Then later on, they have modified, instead of using solid source, they are using metal organics, so the temperature gets reduced automatically, because if it is a solid source, you need to go in for high temperature to vaporize the elements. If it is arsenic, then antimony, then all the third group elements, all the fifth group elements. So, the difficulty involved in individually vaporizing the sources and going in for vapor state species. Then comes chemical beam epitaxy, which is similar to the atomic layer epitaxy. Then vapor phase epitaxy. In vapor phase epitaxy, you have three different categories. That is chloride vapor phase epitaxy, then hydride vapor phase epitaxy, then comes metal organic vapor phase epitaxy. Because yesterday I wanted to discuss all these techniques, but anyhow, so many details are available, so many links are there to understand the basic aspects of this the technique. The issue with the epitaxial growth technique is that LP is not that costly, whereas MBE and the MOEP is a very costly technique, also CPE and the ALE, because though the instrument cost is very high, the industries they utilize only these two techniques for the preparation of optoelectronic device structures. Because for industry, know that you should have high production. So the only out is to go in for these two techniques. And the semiconductor nanostructures can be easily produced, prepared using MB and MO. Okay. So if you compare all this, the vapor phase epitaxial growth techniques, the liquid phase epitaxy is said to be under equilibrium condition, thermodynamic equilibrium, also vapor phase epitaxy, whether it is hydride or chloride. Whereas molecular beam epitaxy, you have what is called as here you need to go in for the kinetics related reactions. Then in metal organic vapor phase epitaxy, you will have to think in terms of diffusion of these the molecules from the vapor phase to the substrate. You see the details in the subsequent slides. So here the growth of this epitaxial layer growth rate is plotted against inverse of the temperature. So you come across two different regions, that is a diffusion based region and the kinetic based region. So in certain cases, we also end up with endothermic or exothermic regions during the diffuse transport. In the case of kinetic transport, see as the temperature increases, the growth rate also decreases. Okay. So when you talk in terms of the vapor phase epitaxial growth techniques, thermodynamics comes into picture automatically. Normally, before you do the growth process, they theoretically calculate the optimum or the approximate growth parameters, namely the partial pressure of each gaseous species to be transported inside the reactor, then the temperature of the substrate, where the reaction will take place, and finally the related species get deposited on the substrate. So here, if you consider the thermodynamics, you come across two different categories. That is the processes, chemical potentials and driving force. The chemical potential mu is important parameter, whether it is the nucleation-based process or the the reaction-based process in vapor phase epitaxy. This the process involves high temperature process, that is the mass transport control, and it is not very sensitive to temperature changes. You'll see in the subsequent slide also what is mass transport and other related parameters. Then it is close enough to equilibrium, so the chemical forces that drive the growth of the species are minimized to avoid the creation of defects and allow for the exact ordering. It is also possible for us to grow superlattice structure using CBE, chemical beam epitaxy, or atomic layer epitaxy. It's the advanced version of MBE or BPE. So it is the basic is from either MBE or from MOE. Okay. So the sufficient energy and time for the species which gets absorbed on the surface. So they reach to the lowest energy state because they lose everything, all the energy, or the Gibbs energy becomes low, duplicating the crystal lattice structure similar to the substrate or their own structure. Say, for example, if it is gallium arsenide getting deposited on any phosphate gallium species, they try to join with arsenic species from arsine, gallium, once again trimethyl gallium. Okay, so the gallium species get attached with arsenic, forms gallium arsenide on the substrate. Either it can be gallium arsenide or indium phosphide or whatever be the indium arsenide, whatever be the cases, but it all depends upon the device structure you try to prepare. Then the thermodynamic calculations I told you, which is necessary before you start the growth process, allow the determination of solid composition based on growth temperature and source composition. It is very important. Otherwise, you keep on, you have to keep on doing the experiment, and it will take its own time to finally reach at least the single crystalline layer to be grown on the substrate. So, this thermodynamic calculation, prior calculation of these parameters, growth parameters, theoretically will help you out to optimize the conditions in cell. And if you think in terms of industries, if you want to grow a particular device structure, say binary, ternary, quaternary, for a particular composition, for a particular band gap, they have the optimized parameters. Yes, they keep on changing the growth parameters for growing various device structures. So it is fixed. Once they optimize, yes. So when you consider the kinetics of the vapor phase epitaxy, the growth rate is controlled by kinetic considerations like mass transport of reactants to the surface. Because one has to understand a lot in terms of the growth rate controlling parameters in MPE or sorry, in MOEPE, because unless you do not understand the real controlling parameters, you will not be able to achieve the conditions for getting lattice matched device structure. Okay, mass transport of reactant to surface, reactions in liquid or gas, reactions at surface, then the physical processes on the surface, that is nature and motion of step growth, controlling factor in ordering, because later on when you think in terms of preparing quantum dots, which normally occurs by self-ordering or self-assembling process, there also we need to go in for the controlling these growth parameters. So the specific reactions depend greatly on the method applied, whether it is MOP or IDDP or chloride UPE. So the reactions depend upon the type of the growth technique we are trying to so here so, yes, So the reactants are dissolved in a molten solvent. This is for liquid phase epitaxy. So let us not bother about it. So in the case of molecular beam epitaxy, I think I will be concentrating more on metal organic vapor phase epitaxy because we have worked a lot in this particular area. Then the molecular epitaxy, it's once again a promising technique, and here beams are created by evaporating the solid source in ultra high vacuum. I think we have enough time to complete. So the evaporated beam of particles travel through very high vacuum and then condense to shape the layer. Okay. So for MBE, the essential condition is that you should have ultra high vacuum up to 10 power minus 10 to 10 power minus 12 torr, whereas it is not necessary for the metal organic vapor phase epitaxy. Right. So in MBE as well as MOEP, you can grow quantum wells, quantum dots, or the modern semiconductor the device success for semiconductor devices like semiconductor lasers or light emitting lasers. And this is a typical skeleton structure of MBE. So here you have various fusion cells, and each cell contain the related elements. Say, for example, if you want gallium, if it is a solid source MBE, solid gallium is stored here, and arsenic, then indium, then phosphorus. So they heat it, then the indium or the gallium, they get vaporized, and it is the vapors are focused on the substrate. If it is metal organic, then the metal organic source for gallium, say triethyl gallium or trimethyl gallium is used. Similarly, for indium and for arsenic, it is arsenic. And for arsenic, it is arsenic. For phosphorus, it is phosphine. They are all very toxic gases to be monitored carefully. And the advantage of MBE is that you have a read screen, reflected halogen electron diffraction pattern can be seen from the read screen. You can see whether the growth is occurring, whether it is crystalline or amorphous. So those details can be monitored. Okay, in the case of vapor phase epitaxy, it is nothing but the specific form of CVD or like PVD. You have physical vapor deposition, chemical vapor deposition. So the reactants are introduced into the introduced as gases. The material to be deposited is bound to ligands. Ligands dissociate, allowing the cell chemistry to reach the surface. You see the typical diagram. And here this typical extron 200 emulsivity reactor, and here for growing indium gallium arsenide or indium gallium arsenide nitride quantum dots, what they use is trimethyl gallium, trimethyl aluminum dopants, trimethyl indium, arsine for arsenic, phosphorus, phosphine for phosphorus, then dimethyl hydrogen for these are all used as dopants, aluminum, indium, right? So the indium gallium arsenide, if it is deposited on gallium arsenide for this composition, for a specific composition, they get lattice measured because the lattice parameter for a specific composition of indium gallium arsenide gets matched with the lattice parameter of say either indium gallium arsenide or indium arsenide. So in that case, the composition plays a dominant role. If it is a ternary on by substrate, because substrates are mostly either gallium arsenide or indium arsenide or indium arsenide, that depends upon the device you are trying to work on. And for the growth of these dots, the temperature is given approximate growth temperature. So what is capping, we'll see later. Okay. That is related to the preparation of quantum dots. Normally, in the case of MOEP, say for example, if you want to grow gallium arsenide, you take either trimethyl or triethyl gallium, and it is mixed with arsine. Arsine is once again a gas. Arsine and phosphine are highly toxic. Toxic. So if you see the arsine or phosphine gas cylinder, it contains 90% of hydrogen and the remaining 10%, maybe in certain cases 5%. The composition depends upon the user. The problem is that if you try to inhale the arsine or phosphine, say 5 to 10 ppb or 10 ppb, it can go up without any issue. That is the toxicity level of this arsine. So the handling is very, very important. Right? You cannot just like that use what we use normal nitrogen gas cylinder. Then for aluminum gallium arsenide, this is what they do. They pass triethyl gallium or trimethyl gallium and arsine, and you end up with aluminum gallium arsenide. And the problem we face in the reactor is that when the carrier gas enters this reactor geometry, here the pressure is very high. Here the when it enters, the gas pressure is very high, and because of the expansion, there is decreasing pressure. So when there is decreasing pressure, there will be the flow difference of this the different gases that enter the thing. And second thing, you have to see whether it is a laminar flow or turbulent flow. You have to control all this the parameters depending upon the flow characteristics. You also get the composition of the deposited epitaxial layer on the substrate. So inside the reactor, you may have either convective flow or depending upon the temperature, the radiative parameters will also come into picture. If it is a convective flow, then the convective currents will create composition gradient, or the pyrolysis reaction will also be different for different species. So you have to initially calculate for this particular reactor geometry what should be the flow characteristics considering the material you are trying to deposit, right? So this is a typical MOEP quartz reactor, and when it is on, it can be heated through IR heating or RF heating or resist heating. That depends upon the temperature. So here the basic process in epitaxial growth is that this rose color or pink color is your substrate, and this blue color, yellow color are the vapor species, that the atoms that comes out of this vapor species. So here you have what is called as deposition, diffusion, nucleation, attachment, detachment, diffusion downstep, the nucleation on top of islands, dimer diffusion, trimer diffusion. So many processes comes into picture. So that is why the thermodynamic the calculation or the kinetic parameter determination for the epitaxial growth prior calculation, theoretical calculation is necessary, and that will avoid so many difficulties during the growth. So on the surface, from the species after pyrolysis, the related atoms move to the surface of the substrate. So these atoms, they form a dimer or a trimer and form clusters. And these clusters, once they join together and they form a layer, it means complete betting is done. In that case, layer growth occurs. And if it is island growth, you get what is called as the growth is not uniform. It is not a layer growth. It is a three-dimensional growth. So if it is a two-dimensional growth, complete wetting occurs. And there are different types of growth modes coming into picture as well as the vapor phase epitaxy is concerned. We will see later. So for predetermining the growth kinetics or the growth parameters for the epitaxial growth, we have used the Serium software to optimize the growth conditions for MOCBD growth. So here what we do is we optimize to the conditions for the particular electron reactor with various growth parameters, and finally we have to optimize the reactor pressure, reactor width, carrier because reactor width is fixed, and we have to modify susceptor temperature, there is substrate temperature, hydrogen carrier gas pressure, ammonium pressure if it is gallium nitride. Because it is gallium nitride, we use ammonia as well as trimethyl gallium, and we have to see the flow rate of these the gases, and depending upon the reactor geometry, we have to modify the reactor pressure, carrier gas pressure, then the other parameters, and come to a conclusion for optimizing the initial growth conditions. So for gallium nitride or Indian gallium nitride, we have to use trimethyl gallium, triethyl gallium, trimethyl indium, ammonia, and the monosilicon for N-type doping, magnesium for P-type doping, and the quantumals are grown under nitrogen main flow and nitrogen bubbled metal organics. So there are various methodologies involved, and the details I am not because the lack of time I will not be able to show the various the parameters, that is with respect to a particular hydrogen gas pressure, but what is the growth rate, and keeping the ammonia nitride pressure flow, what is the growth rate. So all these things we have to calculate theoretical and try to optimize the initial parameters. So based on that, if you start, you'll be able to optimize the growth conditions. And for any semiconductor, you know that the PL, photoluminescence, is a very important characteristic technique based on which you'll be able to understand the status of the band gap. So here, this typical LED, then LED structure. So substrate here is Al2O3, and you have the low temperature gallium nitride to suppress the lattice mismatch occurring at the interface, because aluminum oxide has a different structure and gallium nitride has a different structure. They also use silicon carbide as the substrate. Okay, you see the thickness of the substrate. Normally they use 200 to 300 micron thickness. Then after throwing gallium nitride at low temperature, the thickness of 30 nanometers, they're going for high temperature GaN doped with the silicon. So depending upon the device structure, the number of the multi-quantumals or the gallium nitride varies, right? So during growth itself, you'll have to, before growth itself, you'll have to decide how many quantumal are necessary, what type of doping is necessary, where. Okay? So initially, you'll have to complete all these the basic parameter studies. Now coming to what is called as the growth of the quantum dot. For the preparation or growth of quantum dots, you need to go in for a large lattice mismatch structure. So here, if you take indium arsenide and gallium arsenide, lattice mismatch is around 6.4 to 7%. So gallium arsenide is taken as a substrate. On the substrate, you try to grow the indium arsenide because of the lattice mismatch. There is stress or strain induced at the interface, and because of the stress or strain, right, the layer which is grown on the substrate gets buckled at various places. Under this initial layer thickness should be less than the critical layer thickness. I think the initial stage of the epitaxial growth, I told you that for relaxation of the interfacial stress, it should cross the critical thickness or critical layer thickness. Once it crosses the critical layer thickness, then relaxation will occur, relaxation of the stress or strain present at the interface. So you have to grow this initial layer so that the thickness is less than the critical thickness for this system. That you will have to calculate, right? Okay. So because the thickness is less than the critical layer thickness, the stress or strain is not relaxed. So you will have the stress coming out in the form of buckling, So if you see the growth modes that takes place normally in epitaxial growth, There are three types. One is layer by layer growth, complete wetting, layer by yeah, layer by layer growth. So the substrate, and that you grow the epitaxial layer. So you have complete wetting, and this process we call it as a Frank van der Waal technique. And the second growth mode is island growth mode. It is called Wahlberg-Wimmer. Wahlberg-Wimmer, because here complete wetting is not there. It is also called as 3D growth. So in 3D growth, that will not be complete wetting. You will have what is called as the cluster-like growth or island-like growth taking place. Whereas for the growth of quantum dots, you need to follow Stransky SK method or Stransky Krasner method, where you both layer growth as well as island growth coming into picture. So initially you have one layer grown, which this layer thickness is less than critical layer thickness. This is what I have been telling you in the case of indium arsenic grown and gallium arsenide. Okay, so when because the thickness is less than the critical thickness, you have what is called as the stress being released as buckling at various places. So these islands now you call it as what is called as dots. You call it as dots. Okay, so if the thickness exceeds critical thickness, then you will not have this the buckling coming into picture. So this the typical example is that see here you see this initial layer grown on the substrate is called a capping layer, right? So this is what I told you earlier, and this is similar to what we prepare the puri in our house. So when you the moment you put the wheat the puri on the oil, it gets buckled, right? So similar thing happens here. This is because of the large difference in the lattice constant or lattice parameter between the substrate and the epitaxial layer being grown on the substrate. So you have large amount of mismatch occurring at the interface. So because of the large mismatch, you have large stress or strain coming into picture, and this stress or strain is released in the form of buckling at various places on the substrate. And this buckling comes into picture only when the capping layer or initial layer grown on the substrate is less than the critical thickness. So this condition you have to remember. And here the problem is that the buckling occurs automatically. That is why we call it as self-assembling process, self-assembly, because you would have heard about the SAM self-assembled monolayer, right? Similarly, here it is called self-assembling because it occurs automatically. It occurs automatically. So self-assembling of quantum dots. And the problem is that the buckled the portions or the so-called dots or islands, they will not be able to show you uniform size or shape. So each will have its own shape and size. So that gives us gives lot of problems in the sense the size and the shape decides about the band gap of the material, and also the properties, of course, goes without saying. So if you have different this buckled portions or dots or the so-called islands, then the band gap will also be different. So you will not be able to use this. Say, for example, normally they use 1 centimeter by 1 centimeter substrate, and in that substrate per centimeter square, you end up with per centimeter square in epitaxial growth. That too using MOFE per centimeter square, you end up with 10 power 9 to 10 power 12 dots. 10 power 9 to 10 power 12 dot. So if that is the case, how you will be able to focus on a single dot and try to study its characteristics? And the other issue is that because of the variation in size, variation in shape, variation in the location, you will not be able to go in for a useful device fabrication. Useful device fabrication. So here the another picture is shown to show how this buckling comes into picture. So the strain is around 6.7%, stress is around 5.3 gigapascal, and the thickness is less than 1.1 monolayer, right? So when the thickness is less than the critical thickness, you see, because of the vast stress present at the interface, you have this buckling, and this buckling you call it as quantum dots. So, in plane strain or the epitaxial stress is relieved by the formation of these islands or dots or whatever the cases. So, the lattice planes bulge out at different places. This bulging, you call it as the dots. So, here there are no dislocations, quantum dots are coherent, so that advantage we have. Okay. So the problem with any epitaxial growth technique, whether it is MBE or the what is called as MOEPE, the problem is that the quantum dots nucleate or buckle randomly with varying location, size, and shape. So how to overcome this issue? So you have size non-uniformity, disordered growth. You see the various shapes and the difficulty in accessing the single dot. Because if you want to characterize the characteristics of a dot, you need to have access on a single dot. I told you that per centimeter square you have the dot density varying from 10 power 9 to 10 power 12. So that is the case. How you will be able to understand its individual characteristics. So quantum dot growth by Stransky-Krasnov technique is complex with many probable nucleation sites. So you have to somehow optimize the growth parameters, conditions, then try to the settle the issues. Otherwise, you will have problem with the device fabrication. Though there are so many methodologies suggested to overcome these issues, they were using lithographic techniques, they were using what's called as the stamping technique for growing quantum dots. But the problem is that in epitaxial growth, you will not end up with spherical shaped quantum dots. So that point is very clear. In epitaxial growth, you will never end up with the spherical shaped dots. Only in the case of chemical route, you can have the dots synthesized in the form of spherical shape, not with epitaxial technique. That point you should remember. So that is why for that failure and other things, we're going for the chemical route, then they attach the related ligand or DNA, then the related material for drug delivery. Okay, so that is why chemical route is preferred for this drug delivery application, whereas for device applications, software electronic devices, the epitaxial route is preferred, mostly preferred, as seen in the previous this slides. That is, you can prepare the device structure as per your device geometry. Okay. So you can see the various shapes of the dots, cylindrical, pyramidal shape, uh, but not spherical shape. And they also show different orientation. They also show different orientation. These are the issues one has to overcome. The moment you think in terms of growing dots using epitaxial growth technique, okay. So as the size varies, you have the number of atoms constituting the dots also varies. So band gap also varies. So this the major issue one has to face. Okay. So lattice matched and strained layers. If you consider gallium arsenide and aluminum gallium arsenide, there are different device structures which can be grown using MOEPE or MOME, right? So here, we have done this. We mailed because we mailed on the substrate uh, various indentation using nano indenter. So these are all the indented portion to a particular depth using nano indenter. And when you make indentation, what happens is that you are staining that portion. Right? So when you indent, what happens that automatically dislocations are generated. You'll have to see that these dislocations, they do not interact. So this pitch or the distance between the angle to indentation, you'll have to be very careful. If it is very near, they interact, and finally it will deteriorate the device characteristics. So with respect to time, okay. So here indium gallium arsenide quantum dots thrown on gallium arsenide. So with the various monolayers, that is the thickness of the indium gallium arsenide epitaxial layer on gallium arsenide. So for ml in the sense monolayer, one monolayer is equivalent to 0.28 nanometer. Okay, so 5 monolayer, 5.8 and 6.5 monolayer, you see the dot growth or buckling occurring at different phases. See, this is the bucklings are at random, sizes are different. So see, so you'll have to be very careful. And see, this is the AFM picture, and to focus on a single dot is very difficult. For PL, you know, you'll have to adjust the beam diameter also, the laser beam diameter also, right? So many issues comes into picture. So this is what we have done. You make an indentation. You try to see the status in the cross-sectional term, and now you start grow. You have to optimize the conditions. So this is just like the two horns of the cow or bullock, whatever be the king. See, you see the variation in size, right? So this is a typical array of indentation made on the substrate. Then the growth still there are spurious nucleation in between the dots grown. So this can be easily overcome by suitably adjusting the growth parameters. So this Indian dot grown on the sapphire. Okay. Then the picture shows which are term of single the self-assembled quantum, assembling self-assembled quantum dot in a quantum well for multi-quantum dot LED structure. So the pyramidal shape of the dot is shown here, and here once again cross-sectional scanning column microscope image of this the dot. Here the orientation is very important. Then comes the lithographic techniques. I think I will not be able to concentrate on this, but this focused ion beam technique I told you for slicing the petal, we have used this the technique for analyzing it using them, and for various device structures, the emission spectra, the LED emission spectra is given, and for this particular composition, indium gallium arsenide. The emission wavelength corresponds to absorption wavelength for methane. So from the reduction in intensity, we can calculate how much of methane is present, methane or carbon dioxide or nitrous oxide is present in the atmosphere. So the applications are totally different, because you know nowadays the air pollution becomes very dangerous. So you have to detect through suitable means for finding the concentration of various toxic gases in the atmosphere. So the typical device structures for various LEDs or lasers, right, for growing quantum dot, and the growth timings for we have chosen three samples with various ratios of this indium and arsenic, and the related dot density is given. So for sample A, the dot density is 2 into 10 power 10. Here it is 1.2 into 10 power 10, and here it is 1.4, and the dot size is average dot size is 16 nanometers, and here it is 90 nanometers, and here it is 21 nanometers. And dot size uniformity, here it is worst. This is bad. This is somewhat uniform, but the thing is still the problem is the dot density. Then the corresponding photoluminescence spectra, which is an essential characterization for semiconductors or semiconductor nanostructures. So you have what is called as the quantum dot size effect coming into picture. Okay. This is a typical LED structure for GAN green wavelength emission. Then comes what is called as the issue in LED device structure. It's the simulation work what we have done. So efficiency group is the normal issue faced many of the gallium nitride based LEDs. So the internal quantum efficiency is generated at mm, generally high at low currents. The efficiency gradually drops as injection current increases. So this well-known phenomena called as efficiency droop. Such a droop effect occurs not only in blue LEDs but also in green and UV LEDs. So this issue is to be sorted out. And here so the causes of the efficiency droop or what is called as electron leakage uh, can be sorted out into four different issues. That is, one is carrier escape, and the second one is carrier flow. Third one is poor pole transport. Then the mechanisms, group mechanism, internal losses on the electron leakage. If you consider internal losses, the what is called as OJ recombination, reduced effective volume, carrier delocalization, and in the case of electron leakage, polarization charges, poor hole injection, symmetry, current crowding, electron overflow, defect assisted tunneling, radiative recombination saturation. Okay. So how to overcome this the group problem? It can be through hole injection enhancement, electron confinement improvement, or carrier density reduction. So if you think in terms of carrier density reduction, you have to increase quantum thickness, you have to increase quantum number of quantum bells, then the spreading of the electric current, chip area can be increased. Then the core cell nanorods can be used. And if it is electron confinement improvement, see the engineered quantum barrier which can be increased, right? Say if it is Indian gallium nitride on INGAN, or if it is INGAN on GAN on INGAN, because INGAN means composition will be different. So you will have to you have so many options for improving the group issues. So if it is pole injection enhancement, you have the polarization of barrier level graded electron barrier level, superlattice electron barrier level. Okay, so here what we have done is we have used the Sim LED software coupled with the software tools for LED modeling. So when you do the modeling, you will be able to understand the problems you come across and try to uh, take care of during growth itself. So the saliency is the software, which is a one-dimensional simulator of carrier injection and light emission in nitride semiconductor-based LED structure. So then comes SPEC LED. It is a three-dimensional simulator of current spreading and heat transfer in LED trays. Because when you work on the device structure, you should also know the issues pertaining to the device, and by doing the simulation work, you will be able to get the more details to overcome these issues during growth itself. Then retro 3D ray tracing analyzer of light propagation and extraction in LED dies. Okay. So the saliency, only simulator of carrier injection and light emission, nitride semiconductors gives details about the band diagram, carrier concentrations, electric field radiative, whether the recombination is radiative or non-radiative, internal emission, efficiency, carrier fluxes. So So all the details can be obtained from using this software. So the Synapsys Tricad synthesis tools, these tools are used for electronic design automation that models semiconductor fabrication and semiconductor device operation. And these softwares we have used for designing the device structure. And one of my PhD student, Dr. Victor Robigas, was previously doing a MTech project in Serium project with their PhD here, and she did really excellent work in this particular area. Okay, so these are the different simulation steps for device. So structure, then mesh, generating a grid for numerical computation. Description of physics includes the solution for Poisson equation, current continuity, and the transport equation. These are all physics-based issues. And finally, the results use visualizing the results, both electrical results and internal quantity. So this is how certain issues related to devices are overcome in epitaxial growth. Then we move on to the nanowires or quantum wires. So the nanowires are can be prepared once again by self-assembling process. So actually, this idea was proposed by Wagner in 1960 to grow the quantum dot gold whiskers using silicon as the uh, alloying material. So if you see the basic principle, see silicon and gold, they form static system. Naturally, you have the topic called the phase diagrams coming into the picture. So there are different types of phase diagrams, and even for 3-5 compounds, when you try to form a compound, you should have an understanding of the phase diagram. So without the knowledge of phase diagram, you won't be able to find out which system will form compound, which system will form an alloy. There is difference between compound and alloy. Okay, so in order to prepare the gold whiskers, Wagner what he did was used silicon, because the issue is that silicon and germanium, they mix in the liquid state, whereas they do not mix in the solid state. They do not mix in the solid state. So what happens is that if you choose suitable the composition of this refractor system, what happens is that when you cool the first the gold melting point is less than the melting point of silicon. So gold liquid is formed, and in that liquid the silicon gets dissolved, and from the vapor to keep on growing, the liquid becomes solid, and on top of it, the silicon liquid layer is retained. So this dot is this is your silicon, and in this liquid, gold gets dissolved, and as you as you decrease the temperature, the gold becomes solid. Whereas because the melting point of silicon is higher, still the silicon retains its liquid state. So in this liquid, the gold gets dissolved and the growth occurs. So it is a unidirectional growth. And those days, whiskers seems to exhibit dislocation density to be very less, or even you can say it is dislocation. Okay, that is why people were interested in studying whiskers. But the diameter of the whiskers were of the order of say a few millimeters. Whereas now, because the diameter is of the order of nanometers, we call it as the nanowires. So that is the basic difference. Even now, there are different methodologies involved, and here this is solid, vapor liquid solid mechanism, which is also called as VLS growth, vapor liquid solid mechanism. So from the vapor, you get by condensation liquid formation, and in the liquid you have the solid formation of gold. So you have in vapor you have both gold and silicon. So in liquid you have only the silicon. So this the globules are this cap once you reduce the temperature to room temperature, you have this globule spherical shape retained at the material, and you will not have the silicon in this solid region. That is, you will have only gold. So this can be removed. This portion can be cut off, and this viscere can be used for various series, and it exhibits a particular orientation. So similarly for the nanowires also, the growth is done either VLS or vapor solid or solid solid. Various techniques are used for preparing nanowires, and the these are all the picture, the same picture showing what is called as indium phosphide as well as indium phosphide nanowire. So the size you can see the bar represents 3 micron, and here it is 1.9 micron. So the thickness will be around 30 to 40 nanometers. So they have random growth directions, but the most uniform diameter, because diameter matters a lot. And so if you try to analyze a single nanowire, for example, say indium phosphide using 10, you can try to see whether this nanowire is crystalline or amorphous or say polycrystalline. See here, you see clear cut lines, clear cut lines. It is called the fringes. So if you get the fringe formation in the chart and picture, it means it is a single crystal. It is crystalline, and here you can also measure the what is called as the interplanar spacing. See the, the diameter of this wire is around 20 to 30 nanometers, and this dark portion is nothing but your the globule formed on the tip of the wire. So if it is say I told you in the previous slide as an example, if it is this is your gold, this is your silicon. So whatever material used as solvent, it is retained at the tip or at the top of the nanowire. So this is your indium phosphide. For indium phosphide, used silicon or the germanium. So here the thickness is around 1.5 nanometer thickness, which is amorphous in nature. The interplanar distance is around 0.345 nanometers. So this is called lattice resolved chem image. So you can see beautiful picture of this the nanowire, but it is very difficult to optimize the condition for getting such a nanowire. So here you can see the atomic layers present in the nanowire, and using our the technique also, we have attempted to grow the nanowires. See, we have to optimize the conditions. Still, it is not possible that the array of nanowires which are used for the detectors, semiconductor detectors.